So please join us in giving Dr. Sanders a warm welcome.
Thank you. Thank you. And can I just say I've had the warmest of welcomes from everyone here at the University of Toronto, and especially the grad students. These guys have been absolutely great. So they're sorting out my tech for me now as well. This is fantastic. Are we good? We're good. Amazing. All right. So, good evening, first of all. Thank you, all of you, for deciding to spend this random Thursday night with me to talk about one of my favorite topics, black holes. Woo! I love the enthusiasm. The energy is great. Thank you so much. I'm going to keep that up for the rest of the night, yeah. And in particular today, what I want to do is challenge some of the common misconceptions that people have about black holes and convince you that it's actually not easy to grow a black hole. And that statement often throws people a little bit because people seem to have this picture in their head of a black hole as just this sort of like giant endless vacuum cleaner, with hoovers we would say in the UK, right? Just vacuuming up anything and everything around it. But they're not like that at all. I want you to get rid of this idea that black holes are like vacuum cleaners, all right? I want you to banish little Henry there from your mind and never think of him again. Instead, I like to say that black holes are a bit more like couch cushions in the fact that they're very unassuming. They're sat there in your living room. Nothing is being sucked towards them at all. But if you lose something down the side of there, right, it is gone for good. Right? Just like a black hole. Let me explain what I mean by that. First of all, I guess we have to understand why black holes are black, right? And to do that, we have to understand something called escape velocity, right? It's the reason why if I just jump, now I come back down, right? Because I cannot jump at what's known as the escape velocity of the Earth. Gravity pulls me back down because I can't jump at 11 kilometers a second, right? Or 24,000 miles an hour, if you want it in those units. The only thing that can do that are rockets. I'm incredibly jealous of the person that had this window seat flying over Cape Canaveral. Like, wow. This is why I always pick a window seat on an airplane, just in case. You never know, right? But with rockets, we give them enough energy, right, to either make it to Earth orbit or escape Earth entirely and send them, further to explore the solar system. And the key thing here is that the further you get from the Earth's surface, the escape velocity drops, right? And you no longer need as much energy to get further away, the further away you are. And to bring this back to black holes, a black hole is black because its escape velocity is greater than the speed of light at 299,792 kilometers a second. That's about 27,000 times bigger than the Earth's escape velocity. This is why black holes are black, right? Because nothing can travel faster than the speed of light. We know that thanks to Einstein's theory of special relativity, that nothing can escape. At least, only when it gets too close, right? To understand that, we need to understand how a black hole is formed. So here's our first common misconception as well. Black holes, not holes. Right? If you're picturing like an absence of something, a literal hole in space, again, banish that idea from your mind. I always argue that a better name would be dark star, because they really do start life as stars and then we just can't see them anymore. They're formed from stars, just dead ones. Like technically, I could have a black hole of any mass, right? Like if I were to grab my phone right now and just like squish it down, if I had arms strong enough, I've been in the gym, but I don't think that's still that strong, right? Squish it down until all the space in between atoms disappeared and just keep squashing it and squashing it and squashing it. It became so dense and so compressed into just this tiny speck. Eventually, at some point, it would have a gravitational pull so strong that light cannot escape from it. Be at that point, that bit surrounding that phone that's been squished should be so dense that you would get this thing called an event horizon. It is a sphere surrounding whatever is the black hole in the center, a sort of surface, right? Like how we have Earth's surface, and at the surface, the escape velocity is 11 kilometers a second. At the surface of this event horizon, that's where you get the escape velocity being the speed of light, the fastest speed there is. Like, I'm showing it in 2D here, but like, you gotta remember this is three-dimensional, right? We started off with a three-dimensional phone in the first place as well. And if we got close enough to that 3D surface of the event horizon, like, we'd be trapped there with the matter from the phone forevermore. And if you're thinking, well, that sounds like a terrible idea, Becky, don't take your phone and squish it down to make a black hole because it'll just like suck you in with it. No, it wouldn't really, because black holes aren't vacuum cleaners, right? They're not just sucking things in like all the time, right? This black hole would be the same mass as your phone is that you started with. So the same pull that you feel from your phone now, which I'm like, you probably don't feel any sort of gravitational pull, even if you feel some weird sort of like mental obsession with it, sort of a pull, but that gravitational pull wouldn't change. It would only, when you got too close to the event horizon, that you would become a cropper. And you can work out what that would be as well in terms of, you know, the size of your phone that you start with. My iPhone 13, if we start with it, it's 0.19 kilograms, right? Plug that into the equation for a black hole and you get out 0.000000000000003 meters. Oh, I need a sip of water after that. That's 27 zeros, right? It's absolutely tiny. To put it into context, it is a quintillionth of the size of an atom. Only at that point would light not be able to escape. Then you can work out, you know, at what point a human legging it at like, I don't know, let's say 20 miles an hour to make the numbers easy. Only Usain Bolt could probably do that. But that would be able to escape, and that's still like 0.3 picometers, so 0.3 trillionths of a meter away. So if I could, you know, I'd gladly squish my phone down into a black hole, but I can't because I'm not strong enough to do that. There is only one process that we know of that is strong enough to do this, and that is a supernova. So a star's life is this constant fight with gravity pulling inwards, as like the pressure of the gas in the star is pushing outwards all the time. And that gas pressure is coming from like nuclear fusion in the center of the star. But when that fuel runs out and there's no more hydrogen to fuse into helium all of a sudden, then you've got nothing fighting against gravity anymore. There's light and heat being generated to keep the star shining. And so when that happens, gravity starts to win and the star shrinks in on itself before going supernova. So yes, it shrinks in, but then it rebounds back out again. So here's a little animation of what that might look like. The outer layers rebound off the core because the core is so heavy and they're so light, so they sort of rebound outwards, thrown outwards into this beautiful nebula that we see with, like, you know, the Hubble Space Telescope. And then it's the core, the very core of the star, where all that nuclear fusion was taking place of hydrogen into helium to power the star. That is what collapses under gravity. And what gets left behind depends on what kind of star you started with in the first place. So a star like the sun will give us what's known as a white dwarf. Essentially, you've taken all of the material that was in the middle of the star, the helium that's been left over from nuclear fusion, and you've squished all of the space between atoms until all that space has completely disappeared. So now it's resisting the force of gravity crushing down on it with essentially just like the components of an atom. So you've got the core with all the protons and neutrons, and then electrons that usually buzz around the outside. You've got those electrons just free floating amongst all these like protons, sort of like nicely arrayed in like a crystal kind of shape. And if you keep adding more mass to that white dwarf, if something came along to the sun to just be like, here, have some more mass, right, and started adding more gravity. Or if you started with a bigger star in the first place, something that's 10 to 25 times the mass of the sun, you can see you've got that little thing on top of that, right? The meeting is being recorded. That's great. How do I get rid of that? So you can see what I have on the top here. I don't, we're gonna have to leave that out. Anyway, 10 to 25 times the mass of the sun is the thing you can't see that's hidden under there. If you started with a star that big, instead you end up with what's known as a neutron star. That's now neutrons as tightly packed as they can go, and that's what's now resisting the force of gravity pushing down. But again, if you start with a bigger star, or you just add more and more mass onto that neutron star that you already have, then eventually you'll reach the point where the neutrons just don't have enough force to resist that gravity pushing down on them more. There's not enough energy to resist that, crush of gravity down. And then the neutrons collapse like the white dwarf did before. And at that point, you've made your mass so dense, you've ended up with an event horizon where light can't escape. And you've made what we call a black hole, and we don't really know what happens in the middle of it anymore because we can't get any information from it because all the information we get is in the form of light, and the light can't escape. So did the neutrons turn into something else? Is there a missing stage here that we just don't know about? Some form of exotic matter maybe? Or is everything just compressed into an infinitely small, infinitely dense point that we call a singularity, which is how the maths describes it in the equations? Annoyingly, and I hate to say this as a scientist, we will probably never know if our understanding of the laws of physics is correct currently. We will never know. Ooh, that's annoying. Why did I choose black holes? But hopefully, this picture behind you helps understand black holes just that little bit better, and why I think dark star is such a better name from them. They're just a really special case of a dense object at the end of a star's life. And I also like to think of this as sort of evolutionary phases in a star's life as well. So, if you're a Pokemon fan, I kind of like to think it's just the next evolution in sort of a Pokemon's lifetime. So, now we understand black holes a little better. There's another misconception that I want to help you get rid of. And that is that we can't see black holes because they're black, right? They're dark. We don't get any light from them. But they're not all black. Some of them are actually the brightest objects in the entire universe, which, again, surprises people. Because yes, okay, we can't get any light from the black hole itself beyond the event horizon, but we can tell when a black hole is there because the material around the black hole ends up being incredibly bright. This is how we actually see the majority of black holes in the universe. The material heats up as it spirals around the black hole, so it heats up due to immense friction because it's going so fast as well, and it starts to glow in things like X-ray light and ultraviolet light so that we can see it. So if we actually take an image of the whole night sky, so this is the whole night sky as you look at it, it's the inside of a sphere, which is why it's a funny egg shape. It's kind of like one of those weird projections of world maps as well, because you take a globe and you project it down. But this is the entire inside of the sphere of the sky. And this is it taken in X-ray light. So every dot here that you're seeing isn't a star, but it's a black hole that's got material spiraling around it, glowing, so that we can see it. It's like a smoking gun that there is a black hole there. Now the Milky Way runs along the very center of this image, and hopefully you can see that along the center there is an extra concentration of dots, right? Because you see the Milky Way in the sky, it's this sort of big milky glow of stars that is our galaxy of stars that are a lot closer to us, right? So there we're seeing black holes in our own galaxy. Things that have formed from supernova. There used to be stars there, but now they're black holes. But elsewhere on the image, you can also see we've got other dots of light there as well. That is X-ray light that is so bright that we can see it despite it being billions of light years away, because that's in other galaxies entirely. Not just from black holes that are formed when stars die that are, say, 3 times the mass of the sun to, say, 50 times the mass of the sun, but supermassive black holes. You might remember this image from a few years ago. It got dubbed the big orange donut when it was released, to the press. It's from the Event Horizon Telescope. And this is showing the radio light this time from the material spiraling around the supermassive black hole at the center of the galaxy Messier 87. It is 6.5 billion times the mass of the sun, and the entire solar system could fit inside its event horizon. And again, the reason that we know it's there is because this material that's spiraling around it is superheated so that it glows, so that we can see it even though this is 50 million light years away. It's incredible to think about, right? It's so good that little quirk of physics exists so that we can actually see these black holes and study them. But I have only explained to you one way to make a black hole that forms a black hole, say, like I said, 3 to 50 times the mass of the sun. Supermassive black holes anywhere from 1 million to 1 billion, tens of billions of times the mass of the sun. And so like before, you think, well, you just need to add more mass, right? You just need to keep growing the black hole. You need to chuck more material at it that again gets superheated before it falls into the black hole. Problem is, that's actually very difficult. It is not easy growing a black hole, especially by that tremendous amount. So why is that? Well, first of all, we have to remember that most stuff is just going to happily orbit a black hole. Like in the same way that everything in the solar system orbits the sun, right? If I could right now take my fingers and collapse the sun down in its entirety into a black hole that was exactly the same mass, Earth and all the other planets would happily keep orbiting the sun that was now a black hole, right? We wouldn't notice anything except for the fact that it would be permanently nighttime. We'd probably get very cold very quickly. But they're on stable orbits, right? The planets. Unless you came along and nudged those planets somehow, they are not going to start falling towards the sun. You would have to take energy away from them, slow them down to get them to fall in towards the sun. Because the same thing with black holes, like the sun is not a hoover, the sun's not hoovering things up like a vacuum cleaner, neither is a black hole. It's the same mass, same gravitational pull. So, just like with the planets around the sun in the solar system, supermassive black holes are found in the centers of galaxies, and all the stars in a galaxy orbit them. So this is a series of images. You can hopefully see the date clicking on there in the corner, the year. So it's like a time lapse taken of the very center of our galaxy, the Milky Way. And hopefully what you can see is that those stars are orbiting something in the center. There's also like a circle that comes up that shows you that SO2 star and also its orbit in a little bit as well. And if you calculate how fast all those stars are moving and what their orbits are, you can work out how big the thing is, how massive the thing is that they're orbiting around in the middle. And you find that it's an object that you can't see that is 4 million times the mass of the sun and that can fit inside Mercury's orbit. The only thing that can be is a supermassive black hole. And that work actually won Andrea Getz from UCLA a Nobel Prize back in 2020, for all those who remember it, for measuring that mass. So, all the stars in our galaxy, this is sort of like a Milky Way look-alike galaxy. You are here-ish in the sun and the solar system. It's a Milky Way look-alike because we can't take an image of the Milky Way like this because we're sort of stuck in it. And we can't send anything fast enough to like go up and above it and look down again. You'd have to travel like millions, tens of thousands of light years to do that. And so all these stars are happily orbiting the very center of the galaxy where there's a supermassive black hole, and they are not getting sucked in towards it. They are on stable orbits. And it's not just the stars, it's also the gas that you can see that's like diffuse in between the stars as well. That gas is not going anywhere, and yet that is the gas that's going to somehow grow your black hole and get superheated and glow so that we can see it. So how do you get the gas from nice, happily on a stable orbit, just like the planets around the sun and the solar system, to come off those orbits, take energy away from that gas and somehow get it to fall towards the center of the galaxy, feed the black hole and grow it so it can become supermassive? You need some sort of process that's going to be able to do that. So, what if that process was something really chaotic, like the merger of two galaxies together? That's actually the fate of the Milky Way with its nearest neighbor galaxy, Andromeda, which is actually coming towards us. They're both beautiful spiral galaxies now, but in a couple of billion years' time, they're expected to come past each other in a close pass, sort of slosh around a little bit before they fully collide, merge together, and make one single galaxy. And in that process, that's the kind of thing that can shift stars and gas around. You can see how the shape of the galaxy has changed that you get in the end. It's no longer one of these beautiful spirally things like we saw on the previous images. It's just a big blob of a galaxy now, right? Just one big giant sphere of stars. Basically what you've done is you've taken the galaxy and you've scrambled it up until a lot of that material, a lot of that gas that was on nice stable orbits before has had all its energy taken away and redistributed, and it's sunk towards the center. And that, okay, was a very chaotic and catastrophic thing to happen to the galaxy. And that's really what happens if you have two galaxies that are roughly the same size that might come together and merge. But if you have something that's a bit smaller, say like the galaxy in the top right corner that you can still see there, that's the Triangulum galaxy, another of Milky Way's neighbors, but it's a lot smaller than us. If that came in and merged with us, it's kind of like, you know, dropping a pebble into a pond. There would be ripples through the galaxy, but really what would happen is you'd kind of like form a mini version of this just in the center, and you'd like keep the nice spiral structure around the outside. Be kind of like, if you want to picture it, it's like a fried egg, right? You've got like nice spiral structure, which is the white, and then you end with a big blob in the center, which is the yolk. And we see these mergers happening across the universe, right? These are like little snapshots that we get with the Hubble Space Telescope. So annoyingly, because these merger processes take like billions of years, we can't watch them happening. But thankfully, there are galaxies in different stages of this process as we look in all these different directions in the universe. And these allow us to put together a picture of these snapshots of what's going on. And when we have a merger like this, right, we talk about, okay, well, it'll tumble gas in towards the center to grow the black hole, but you think about it, it'll also grow the galaxy too, right? You like double the mass of your galaxy if you merge with another thing. So if you're going to go and be like, okay, how heavy is the galaxy in terms of how many stars it's got, then that's also going to grow. Which means, ladies and gentlemen, we have arrived at the first plot of this talk. It is a plot. Oh, that was bright. I'm so sorry. I should have warned you. That shows what I was just talking about. So, on the x-axis of our very first plot tonight, we have the mass in stars of a galaxy central, what I'm calling a bulge. So the yolk that I was just talking about in that like egg white and yolk situation of a galaxy structure. And on the y-axis, we have the supermassive black hole mass. And you can see there's a nice correlation there, right? If you grow the galaxy, you grow the supermassive black hole. And so that whole story that I just told you about needing some process to scramble things up in a galaxy and send gas tumbling towards the center, that coming from a merger, that whole story I told you basically came from this plot, right? This correlation is what made people realize, right, if you have a merger of a galaxy, you grow this big bulge in the middle, this big yolk structure in the sort of galaxy structure. Or you make one big blob entirely that's like all bulge. And you grow the supermassive black hole. Perfect. This is something we're going to call co-evolution. The galaxy and the black hole evolve together in this process of galaxies merging. And so everyone was sort of like, oh, we've cracked it. What a really nice, little, neat sort of picture of what happens, all tied up with a nice bow on top. We figured it all out. But then, me and my research group started asking questions that sort of just rocked the boat a little bit. Because we were like, well, what happens in galaxies that have not really had a merger? Because like the Milky Way galaxy hasn't really had a merger, or at least not a big one in the last like 10 billion years or so. So what about those kind of galaxies, right? Like Andromeda there on the left-hand side, beautiful example of what I was just saying about the whole like picture a galaxy like a fried egg with the yolk in the middle. That's the big bulge of stars, like a big sphere of stars in the middle. And then the sort of spiral on the outside is like the egg white. What about the things that don't have a bulge? The things that probably haven't had a merger because they don't have a bulge. They've been left alone their entire lives, so they have this beautiful like spiral structure, and that's all there is to them. What about the black holes in the middle of those things? What you could call, if you were inclined to do so, the egg white omelette of the galaxy world, right? There is no yolk there whatsoever. Most people, when we spoke to them about this and raised this question, were like, they're probably small. They're probably not very massive at all. And we were like, has anyone actually checked that though? And we realized no one actually had. So this is what my research topic is now, and I kind of want to explain what we've been up to, if you're up for that as well. So we had to go away and find these kind of galaxies. These galaxies that have never had a merger. So they are pure like disk galaxies, these egg white omelets, right? They clearly don't have this big blob of stars in the middle. And we went and looked in a big survey of the sky. It was taken by the Sloan Digital Sky Survey with a telescope in New Mexico. And from 1 million galaxies that it targeted, we found 100 of these things with growing supermassive black holes so that you could actually see the black hole and measure its properties from the gas around it. You can actually see the black holes in these images. Can you see those really bright spots in the middle that are a slightly different color to the starlight in the galaxy around them? They're kind of purplish. That's the light from the material spiraling around the black hole. And that's what we were looking for. Now these images are taken from the ground, so they're a bit fuzzy, and you're like, oh, I maybe thought those big purple dots were maybe the bulge when you first showed them, Becky, and you were like, yeah, okay, fine. You could hide a bulge underneath them, but once we found these, we then got to use the Hubble Space Telescope and get really, really, really cool pictures of these galaxies and show that there really wasn't any bulge, and all we really had was these beautiful big spiral arms, and maybe even a big bar. You see that like long, thin structure running through the middle? And then, again, that bright point in the very middle that's the glowing gas around the supermassive black hole. And so what we wanted to do with objects like this was say, okay, let's measure how heavy the galaxy is in stars, and then also go and measure how heavy their supermassive black holes are to test this idea of what happens in these galaxies that have never undergone a galaxy merger before, the way that we think galaxies and black holes co-evolve and grow together. So that means that some poor person has to go to the Canary Islands to go and use the telescopes there. It's such a shame that I have to go to the Canary Islands. I just want to put some context to this photo that some people don't really notice. Behind me, that's the clouds that I'm above, which is great for astronomy if you're above the clouds. You're so high up that you're essentially you're above that sort of cloud inversion. You can see the other telescopes behind me as well. One of them that's sort of opening a little bit like Pac-Man to like stare at the sky. You can see they sort of have, in the top left one there's like a little bit that opens up to let the telescope sort of poke out, and that whole big dome structure moves so that you can see it. Also, the sun is setting behind me. I'd just eaten breakfast about when this photo was taken, because you obviously have to shift your hours if you're an astronomer working at night at a telescope. Midnight lunches are very fun, I have to say. This is the telescope that we were actually using, so that photo that I just showed was sort of taken on that big sort of bit on the right-hand side that's sticking up. To give you context, that's a 4-story building with a huge big dome on the top that's inside it, a 2.5 meter optical telescope called the Isaac Newton telescope. The fun thing about this telescope, and I use fun in the loosest sense of the word there, is that this building was built in about the 1970s. It was the only telescope on the top of the island at the time of La Palma, and so they had to build everything to house astronomers, like bedrooms and kitchens and bathrooms and libraries so you could work in there. But since they've built like a centralized system to house everyone who's using all of the telescopes, like a big dorm kind of situation. So now you're essentially working in the control room with 4 floors of an abandoned 70s building below you. And that's where your bathrooms are if you need a loo in the middle of the night. And you also have to keep all the lights off for fear of like ruining your observations and any light leaking outside. So you have to move through this abandoned 70s building in the dark at like 2 a.m. while you're desperate for the toilet. It's almost like you can hear this like room full of people that are clearly watching the horror movie that you're currently starring in, screaming at you to turn on a light. It's terrifying. But it's worth it because we got data. So, what data were we actually trying to get? Well, what we were trying to do was observe the glowing gas that's spiraling around the supermassive black hole, what we call that accretion disk. Most of that material is hydrogen, which makes things nice and easy for us. So, in a physics talk, we're going to do some chemistry, guys. Chemistry 101. Do we remember the hydrogen atom is one of the simplest atoms we can get. It's a proton in the very center, orbited by an electron around the outside. And if we pump some energy onto that hydrogen atom, like for example, because the accretion disk is glowing because it is hot, then that electron will be like, "Ooh, thanks for the energy," and jump up to the next place it can orbit around the proton that it's allowed to. Just needs more energy to do so. And it jumps up, orbits there for a while, and then goes, "That was fun," and it drops back down. And in that process, it gives out light. Now, because those orbits that it can orbit around the proton, they're only allowed at very specific levels, which means very specific energies. There's always the same amount of energy that separates that a bit that it jumps up to and comes back down. So the light that's given out always has the same energy, which means it always has the same wavelength as well. So there's a big, bright spike in a very certain wavelength from hydrogen that's orbiting around black holes. So if we can take that light and split it through a prism, for example, so we get a nice rainbow of light and make a trace of how much light of each wavelength you receive, then you get a nice spike at that specific wavelength that hydrogen gives out. So, we've already had the first plot, so I know you're very prepared for the second plot, and don't worry, this one's not white, so it's not going to blind you. this one's nice on the eyes. So this is what this would look like when we plotted it out, right? You would have wavelength on the x-axis, so like the color of the light or the energy of the light. You would have the amount of light you're receiving on the y-axis, that we call the flux. And what you'd expect to see is this giant, whopping big spike at the wavelength, the energy that we know a hydrogen atom gives out. Great. The problem is, that's not what we see. Or I don't want to say problem, it's actually a good thing. That's not what we see. I'm about to put up some real data that we took with the Isaac Newton telescope of the hydrogen spiraling around a supermassive black hole. That's what that white squiggly line is there. It's noisy, which is why it's squiggly, because there's all sorts of sources of noise getting in the way, the atmosphere being one of them. How annoying. But then also you've got to fit to that data. So that's what that cyan line is that's running through the white, and then what I've just done is shifted it down so you can see the shape that you get, right? That's what the red that is showing. And hopefully what you can see is that red line is not that super sharp peak that we were talking about before. Instead, it's sort of been smeared out, right? It's been broadened. It's not super sharp. So why has that happened? Well, maybe some of you might have picked it up in sort of what I've been saying, the language I've been using. I've been saying this hydrogen gas is moving. It's spiraling around the supermassive black hole, which means some of it is coming towards you, and some of it is moving away from you. So it's been Doppler shifted. Right? We all hear these Doppler shifts during the day, right? As cars or ambulance sirens race past us on the street. As they come towards us, an ambulance siren sounds a higher pitch. Because as it comes towards us and releases the sound wave, that sound wave gets squished as the ambulance moves into the wave. And then as it moves away from us, it stretches out the sound wave, and then we hear that as a lower pitch as the ambulance races past. The same thing happens to light waves as it does to sound waves. So as the light comes towards us on one side of the disk spiraling around the black hole, it gets squished. And it gets squished to a higher wavelength, a bluer color of light. And as it moves away from us, it gets stretched out to a longer wavelength, a redder color of light. So on the left-hand side there, you've got light that's been shifted to bluer colors, and on the right-hand side, you've got light that's been shifted to redder colors as it spirals around. And do you remember before I showed that really cool time lapse of the center of the Milky Way with the stars orbiting around it? And I said if you can work out how fast the stars are moving, you can work out how fast the thing is that it's moving around. And from this, from the amount it shifted, we can work out how fast the gas is moving around the black hole, and we can work out how big the black hole is that it's moving around. Can we just take a minute to appreciate how freaking cool that is? Like, I was amazed that I was a person working in astrophysics was, doing this as a day-to-day job. That blows my mind every time I do this calculation. But also that just we as humans have figured out how to do that. Like, think about how many advancements in science had to happen to bring us to this point. Right, we had some chemistry in there, we had some quantum physics with those energy levels and working out, how much that energy differed each time. You've had to have engineers that have figured out instruments of how to do this as well. Right, there's so much physics, as well as figuring out that even supermassive black holes live at the centers of galaxies. So much physics, chemistry, that has to pile up over the centuries for us to be able to do this now. I don't know, I think that's pretty cool. Gives me goosebumps just thinking about it. Because I hurt your eyes last time, I'm going to warn you now, we're going back to a white slide because we're going back to that plot that we saw before. So I don't know, you're going to close your eyes while I do it. Do you remember we had this plot before, right? That motivated the whole reason that I had to go to La Palma and I had to measure these cool black hole masses, and what a shame. Is because we wanted to see where these galaxies that had never had a merger with another galaxy lie on this plot. So shall we put them on there? Let's do it. And you're probably thinking, why are they all arrows, first of all? Well, do you remember that big, bright point of light in the middle of the galaxy I was getting to look for before? I said it was that purplish blue color, right? That was the light of the black hole that you could see, and how cool was that? It's very cool, but you could also maybe hide a bulge of stars under there. So we kind of have to take that into account. And to put it on this diagram, we have to be like, it could be that there's a bulge this big under there, but it's probably smaller than that. So they're all arrows because they're all going to shift this way some amount, but we don't really know by how much, right? So we put them on there as arrows. But at the same time, even if they weren't arrows and we just put them on this diagram, they're no different to the other things, right? In fact, if they were all going to shift, that super nice correlation line that's in the red dashed line there, they'd be way above that. And yet, galaxy mergers are the things that we think grow supermassive black holes. And these have never had a galaxy merger. What? What's going on here then? And if you want to take into account the fact that these are all going to shift somewhere, and you want to put a nice line on there, maybe that's like, here's where the bulgeless galaxies probably are. They're in that sort of like bow tie shape somewhere, right? I mean, you could put a vertical line in there for all I care, right? There'd be no correlation whatsoever. So what is going on here? Thankfully, also, we have some simulation friends. Remember I said before, with the universe, you can't really watch these things happen. You just get snapshots. Yeah, it's kind of annoying, but simulation friends, they're on simulations where you can kind of watch this happen, you can get this information, and they can measure how big any sort of bulges that's under there, what is it, and we can kind of see, thanks to simulations, where they'd shift to, right? That's what the simulations give us. The really cool thing about simulations too, is that they can tell you where all the stuff in black holes has actually come from, when they throw all the laws of physics in there and they, simulate the entire universe evolving. If they do that, and we track which things have grown black holes, and on the x-axis here, right, we've got we call redshift, right? So it's kind of basically how far away things are, but also because light takes time to travel to us, we're seeing the early universe. So when we look at simulations as well, we can say what's going on in the early universe and what can we see, what's going on today, right? And we can track that growth over time. So there's time here on the x-axis. I know it's shifted. They're simulation people, they're weird, right? Don't question it. So we go, right, and we say, look at that red line there. That's all from mergers, right? That's all the stuff in black holes that's come from galaxy mergers. So that could be the two black holes in the middle merging together. It could be all that gas that's been scrambled up and sent to the middle. And you can trace it all the way to this side, to where we see today. And you can read that number. You get to about 35% of all the stuff in black holes comes from galaxy mergers. The rest, not mergers, which is basically what we also found, right? That in things that didn't have mergers, you could grow them as big as 1 billion times the mass of the sun. And when we turned to our friends in simulations, they were like, oh yeah, it turns out that thing that we thought was the only thing that grew black holes only accounts accounts for about 35%. So this was a bit of a shock, really, to a lot of us. And a lot of my research now is trying to figure out, well, if it's not mergers, what is it then? And also going around conferences and trying to convince people, hey, that picture we all had in our heads of how black holes and galaxies grow, turns out it probably wasn't quite right. Obviously still happens, 35%-ish of the time. The rest of the time it's something else. And there's one other problem, because not only do they seem to not grow like we thought, but the rates we see black holes growing at, there's not enough time to grow them that big. The James Webb Space Telescope is finding supermassive black holes of 1 billion times the mass of the sun at a time when the universe is only about 500 million years old. How you grow a black hole that big in that time, we just don't know. So there could be another way entirely that you could form a black hole that's not from a supernova. It could be that you get a cloud of gas in the early universe that just collapses straight down into a black hole. And JWST is trying to find signatures of this actually happening. I'm still waiting for them to tell me what they found, but we're hoping it will come very, very soon. Is there another way to even start with a black hole growing and get a bit of a head start? So, how do black holes grow? Well, we learned first of all that they are not vacuum cleaners, right? That was the first thing we learned today. All these misconceptions we threw out. We learned that some of the time, about 35% of the time, it's probably when two galaxies merge together. That's how black holes grow. They scramble up all of the material, send it tumbling to the center, and the black hole goes, thanks very much, and grows heavier and heavier. But then the other 65% of the time, it seems to be merger-free. In the absence of galaxy mergers, something else happening, something inside of the galaxy itself, maybe funneling gas down those beautiful spiral arms that we saw down to the black hole, slowly but surely. Not so chaotically as in a merger. We're still not quite sure of what the exact process is, so maybe I should come back in like 5-10 years' time. We've done a bit more research, and hopefully we can update you. But if there is one thing that I want you to take from this talk today, is that black holes are not endless vacuum cleaners, but they're more like couch cushions. Thank you very much.
Thank you, Dr. Becky, for the amazing talk. And now we're going to have a Q&A with the audience. So if you have any questions, please raise your hand.
Hi.
Just a question. You're looking for the other 65%. And we know dark matter is a halo around both galaxies. So has the simulations looked into the dark matter as potential solution to this?
So, funny you should ask this, because I had this exact thought during the write-up of my PhD when I was possibly a bit frantic whilst writing up. And I was like, could it be dark matter? Could it be dark matter growing the supermassive black hole? And I left my office, ran down to where I knew my friendly simulation friend works, which is he's actually sitting right here, and I haven't seen him in about 5 years, so I'm very excited to see him. And I literally came into his office like, could it be dark matter? Like in my anxious state. And Mark, bless him, had to be like, no. The problem is with dark matter, it's what we call collisionless. So I don't know if you've ever seen that really famous picture of the bullet cluster where it comes together and we see that the galaxies go through each other and the mass distribution that we know is there, the dark matter goes through each other, but then the gas in the middle collides and you see that light up in X-rays. So we know that dark matter doesn't really collide with itself. And the thing is, in that accretion disk around the black hole, the way that the matter eventually gets into the black hole is it collides, one particle loses energy, and therefore falls into the black hole, and the other one gains it and moves out in the accretion disk slightly. So it's through those collisions that eventually material will fall in, otherwise again it will just keep orbiting it. And because dark matter is collisionless, there's no way for it to really get into the black hole.
Get in through accumulation as the black hole wanders around through the halo.
I mean, if you have it on like a direct course, but I think, if I remember right, Mark, I think you put like a number of like 10% on it in simulations, like maximum limit, like, yeah, you'd struggle even to get that. So great question, thanks.
You said that, toward the later part of your presentation, you said that James Webb is looking for signs of gas falling in a collapsing American black hole.
Yes.
Was that a reference to primordial black holes? And if it is, do you think that's a possible theory?
No, so primordial black holes are something completely different entirely. That's like, you know, first couple of fractions of a seconds of the universe's life when it's incredibly dense, and you can get random like quantum level fluctuations that just get dense enough with like a clump of things that could form a primordial black hole, where we're talking like, it could just be a couple of atoms up to like, you know, Earth mass or something. These direct collapse black holes would be like 10,000 times the mass of the sun, right? They're a huge cloud of gas. No evidence for primordial black holes yet. And again, still no evidence for direct collapse black holes either yet. JWST is kind of looking for the glowing gas just before it will collapse.
Let's also take some questions from the back. Who has a question here?
Now, could a black hole raise itself as only the Big Bang that happened?
So, no, we don't think so. However, have you heard of something called a white hole? Which is like the exact opposite of a black hole in its entirety. And this is a completely hypothetical object. We don't have any evidence of these existing. But essentially, if you think about like, you know, when you're going towards a black hole, there's no other point in space or time that you could end up in, right? It's inevitable that you end up like inside the event horizon and the singularity. A white hole is the opposite, right? Where it like spews stuff out because there's no other, you know, direction of space nor time that you could go in that wouldn't send you away from the white hole. And so people have sort of hypothesized that maybe you could explain sort of like the beginning of the universe kind of as like a white hole in that respect, but the math still doesn't quite check out. But then there's all sorts of weird and wonderful theories, like the center of a black hole is a white hole, or the two are linked in some way by some sort of bridge. And so there's loads of ideas like that, but I think the problem is that our physics still breaks down in those first early fractions of the seconds of the universe, so we still don't really know and don't really have any maths to describe it. We way at the back now, Jenny? Or I can't see where she's
We
going.
have a question right here.
Oh, great. Oh, hi.
Have you discarded any theories about what the 65% is? And if you have, can you tell us what that theory was?
Sure, yeah, so there's a couple of ideas that we have. So one hypothesis is it's that bar structure, you know, that long thin thing I pointed out before. That moves around the galaxy and could drag gas with it and down the bar. Same for the spiral arms, they could sort of wind in and take gas with it towards the center. But then also, have you heard about the idea of the cosmic web? There's this structure, if you plot out sort of like all the galaxies that we see at the distances and make sort of like a 3D map, you get sort of like the structure of the universe slowly building up and building up. And it looks like a big sort of sponge or a web, right? You've got these big gaps and then all of these sort of filaments connecting all of the galaxies together that could have gas in them as well. So one idea is that gas could come from those filaments and end up in the center of the galaxy, again in a very slow process. The problem is this is all based on like simulations and, you know, sort of like theory. So we have some numbers from those which we can match to sort of like what numbers we see in terms of to account for like the growth of the black hole rate and think, okay, well, they kind of match, but we're trying to pin it down in observations. It's just very difficult to do that because you need lots of different types of observations to do it. You need to observe it in a sub-millimeter wavelengths that gives you the amount of gas you've got there. You need to observe it in optical wavelengths to look at the velocities of things that you've got there and the amount of gas you've got there as well. So many things that need to come together, and they're very expensive observations in both money and time is more what I mean as well. But slowly but surely those pieces are coming together, and there's even people here at the Dunlap Institute that are working on that with me. So
We have another question from the back.
Hi.
hi.
So, quick question about the dark matter. So far, as of, let's say, 2024, how much information do we have from dark matter that we can use in favor of us human beings in our missions.
In favor of what? Sorry, could you repeat
In
that?
favor of us, like, so in my point of view, I'm doing aerospace engineering, and what I'm thinking is that instead of having a thrust or an engine, we can use kind of dark matter and reactions to help that rocket move, in my point of view.
I mean, that would be great if we even knew what dark matter was. I mean, I think from an astrophysics perspective, we have got a lot of evidence for it now. In so many different places, from our observations where we can see there's matter there, but we can't see any starlight or any other light that could account for that mass that we see. Or, you know, the galaxy cluster colliding that I was talking about before, or even running simulations of galaxies and just getting them to form, you need this cold dark matter there to make it, to produce a structure like what we see today in the universe. Basically, as astrophysicists are sort of looking at our watches and looking at the particle physicists like, come on guys, you've had enough time. What is it? And I think their ideas, right, I don't mean to pick on particle physicists, they're doing a great job. You know, their ideas are sort of like, you know, it could be this idea of, you know, you take the standard model and you've got these symmetric particles that they call supersymmetry, that's this idea of axions. There's nothing been found as of yet, so people are looking into other ideas, like could it be primordial black holes that is dark matter, or, you know, could it be that we haven't got gravity right and that Einstein is wrong and we need to tweak gravity and there is no dark matter there? There's people been working on that for years but hasn't found anything. So it's not like we've just sort of found the evidence and like walked away from it. We're thinking a lot of other things too, but I think we're a long, long way away from thinking about dark matter as like a propulsion. So.
Thank you.
Do we have other questions? Oh, yeah.
I've got a question here. Sorry, take that back. Much of the literature that I used to read back in the 80s was discussing, this was back when the horizon was probably known more as a Chandra star, the solar mass expectations for black hole possibilities was on the scale of, let's say, 1.4 solar masses. I noticed in your material that we've significantly upgraded that mass requirement. What are some developments that led to that realization?
I mean, the Chandrasekhar mass is that limit at which the white dwarf becomes too massive and it collapses down into a neutron star. When Chandrasekhar first estimated that back in the 20s, 30s, he was way under that 1.4 mass limit. I'd say it wasn't even the last 40 years. Like, I mean, the limit of a neutron star is known as the Tolman-Oppenheimer-Volkov limit, TOV. If anybody saw the film Oppenheimer last summer when it came out, that very first scene they have in the classroom is them figuring out the Tolman-Oppenheimer-Volkov limit of a neutron star collapsing into a black hole. So that's like late 60s, but again, that wasn't probably quite accepted until a lot later, until there was observational evidence for a black hole in the 80s, for example, as well. So I think it was a lot of the observational evidence in the theory of like neutron star structure that really pushed that forward and ended up with those limits of, you know, collapse to a black hole, like 3 solar masses, basically.
What surprised me is that, you know, a G-type star, a heavy-duty G-type star could collapse in a single stretch in the night. Thousands, I don't believe the answer to that question.
Thanks.
Hi, I have a question.
Oh, where are you? Wave at me, I can't. Oh, hi.
I have a question regarding the fact that we know the space is expanding, and specifically regarding the 35% theory that you mentioned that the black holes are expanding because galaxies are merging. So I want to know if the fact that space is expanding, has been expanding for a while, does that have any effect on the rate of growth of black holes, and any effect on like in the future of new black holes going up?
Yeah, it's funny you should say that, because about, was it last year, 2 years ago? I can't remember now. There was a paper that came out that was like, are black holes dark energy? And dark energy is the name that we give to the thing that causes the accelerated expansion of the universe. And I'm going to hold up my hands and say, honestly, it was the paper that hurt my head the most that I've ever read. I didn't quite believe what they were arguing. They laid out the mass, they laid out the theory, but then the observational evidence they used to prove it was based on that black holes grow through mergers. So I was like, I don't buy that, because I know they don't. So I don't think it's necessarily that, and I wouldn't say no that sort of like a black hole growth has anything to do with the expansion rate of the universe, because, I mean, growing a black hole, you're growing its gravity, and that's acting in the exact opposite direction as the expansion of the universe, which was like a negative pressure outwards, so.
All right, we have a question over here.
Oh, okay.
Hi
Hi.
there.
I was wondering, when you were talking about like bars in galaxies, I was wondering if there are any direct observations or any sort of evidence in that case of like larger growth in supermassive black holes when there are bar
So my research group is sort of working on this, like the extended research group. So someone called Izzy Garland has looked at this, where they've looked at if you have, you know, a bunch of barred galaxies and a bunch of unbarred galaxies, what is the fraction of growing supermassive black holes in both of those? And you find that, there are more growing supermassive black holes as a fraction in the barred things than the unbarred things. But that has been a bit of an argument in amongst astronomy communities for a long time. You had to control for a lot of things. She did it really carefully and showed that yes, actually when you do that, you find that there's that extra fraction of growing supermassive black holes in barred galaxies that could be that connection we've been talking about. Yeah, great question. There's waving and pointing, I don't...
Okay, good question here. Are there is there a limit to how large a black hole can get?
Yes, great question. I love this question. So, we think so, yes. And we think that it's around, and this is, you know, as precise as we can get as astronomers, but it's like 50 to 100 billion times the mass of the sun. And it all depends on the properties of the black hole and the spin and things like that. But that accretion disk, at some point, you can collide as much as you like in the accretion disk, but you won't lose enough energy to actually get close enough to how massive a black hole gets to end up helping to grow it. I actually have a whole YouTube video on it if you want to deep dive on this. It's a great video, I'm just saying. You should go home and watch it. But essentially, you can think about, black holes as causing these big sort of we call them gravity wells, as how much stuff will get drawn in. But the bigger the black hole gets, the less steep it gets. So if you want to think about it like a mountain, very less massive black holes, they have very sharp peaks, even though the peak isn't very low. So very gradient up to the top would be very sharp. But then a massive black hole, supermassive one, it's more like a really tall mountain that's really, really, really gradual sort of gradient. And so the gas doesn't really get to it as easily as you get to those masses. So we think it's around about 50 to 100 billion times the mass of the sun. And we've actually found one that's around about 60 billion times the mass of the sun. And we're like, are we reaching the limit that black holes can grow to now? Which would be pretty cool. Where are the mics? I see the mic rovers moving.
Yeah, I see a question here.
Oh, yes. Hi.
I'm sure you're familiar with Stephen Hawking's work with black holes.
Very.
He theorized that black holes would shrink.
Evaporate.
Due to a loss of radiation. So how does that jive with nothing being able to escape?
Yes.
Black hole?
I have to be honest with you, this is probably the worst question that I think anyone can ask in a public setting. Because it's so difficult to explain Hawking radiation without equations. It is the thing I find the hardest. I tried in the book. If anybody's read my book, A Brief History of Black Holes, there's a whole chapter on it where I tried, and I hope it made sense. The problem is with Hawking radiation is that you start to involve quantum effects. And we don't actually have a theory of both quantum effects and gravity. Frustratingly, right? No one's been able to combine those two things. And Stephen Hawking was basically like, I don't need to combine them. I can take a shortcut and figure it out this way instead. And by doing so, he managed to sort of figure out that black holes would have almost like a radiation to them, this Hawking radiation. And essentially what happens, and this is paraphrasing as much as I can because I know we've got many questions, is that you get this sort of particle creation at the event horizon where one particle shoots off and escapes as Hawking radiation, and another particle ends up back in the black hole anyway. And it's like the energy of the black hole interacting at the quantum level that produces these particles, and one goes off and escapes, and that takes some energy away from the black hole. And as Einstein told us, E equals mc squared, energy equals mass essentially times speed of light squared. They're equivalent, so if you take energy away, you take mass away, so the black hole technically shrinks. But the time scale this happens on is like longer than the age of the universe. And so people have worked out that maybe like, you know, a black hole about the same mass as like an asteroid or something might have evaporated by now, but something like a supermassive black hole, nowhere near. If I can, you know, maybe encourage you to read the chapter in the book, it might give you more info.
We have a question up here.
Wave at me. Oh, great, thank you. Hi.
Hello. I know we were talking about growing supermassive black holes by like chucking mass at it, chucking matter at it. And forgive me if you mentioned this and I missed it, but I know I've heard a bunch of formation theories about supermassive black holes forming through mergers of stellar mass black holes, or like anti-main mass black holes, which are another species of black hole we don't really know much about.
Yeah.
But so I was just wondering what the logistics of that, the probability of that versus, you know.
The direct collapse I was talking about at the end? Yeah. I mean, yeah, there's lots of ideas that in those early stages of the universe, so in the first like billions of years, maybe you form like some sort of like globular cluster of stars that maybe a lot of those big ones, you know, went supernova, formed a black hole, all of them sank to the center, would merge together, and that would be that first initial stage of growth. But as far as I understand it, you still need some accretion in those early days of the universe, some gas being funneled in to get the kind of growth rates that you would need. You can't just do it with mergers alone.
Okay, thank you.
Yes, thanks.
We have time for 2 more questions left.
Hi there.
Hi.
I'm just curious, right? If the gravitational pull of a black hole is so strong that it pulls everything in, and why are there still stars and galaxies circling around? Why aren't everything sucked in?
That's a great question. Again, I have a whole video about this that you can go watch, but essentially we're all here in the first place and galaxies all exist because of something called the self-gravitational radius. So at a certain distance away from a black hole, the gravitational pull between, like, say, 2 gas particles in a gas cloud is greater than the pull they feel from the black hole. And that's not that far away from the black hole, astrophysically speaking, in terms of like galaxy scales, which is why, you know, gas particles in a gas cloud will collapse and form a star rather than getting slowly, inexorably pulled towards a black hole. So we have to be very grateful for the self-gravitational radius, otherwise none of us would all be here.
All right, we have one last question over here.
Oh, yeah, hi.
Hello. So, talking about Stephen Hawking reminded me of something I've read where apparently Stephen Hawking said like extremal black holes are impossible, but I read somewhere that some mathematicians have proven that they are not impossible. So I was wondering what extremal black holes are, like, and what's up with that.
Can you say that word again? What are you saying?
Extremal.
How are you spelling that? Sorry, I've never heard that phrase before. So
Extremal.
I have never heard that phrase. Mark, have you heard that phrase? No. I don't know. I don't know what that is. Maybe that's some of Hawking's work I'm not familiar with. I'm sorry, but I don't know that phrase to answer that question. I'm so sorry.
Do you want to take one more quick question? Or
2009.
I guess we can take one more quick question.
I have one more question right here.
Oh, okay.
Hi, thank you for a wonderful talk.
Oh, thank you.
On the chart where you have the intensity of light and the wavelength of you're measuring what wavelength of light intensity is up, why is it asymmetric?
Why is it asymmetrical? Yeah, okay, there was like a little bump, wasn't there, on one side? Yeah, okay, so that was nitrogen also emits at a similar wavelength close by to hydrogen. And so if you didn't have the black hole there, you'd see 3 very distinct peaks. A taller one from nitrogen, the really tall one from hydrogen, a slightly smaller one from nitrogen. There's 2 nitrogen bumps either side, one is slightly taller. And so when you add that all together on top of the big broadening that you do to the H alpha, it ends up being ever so slightly lopsided. Good spot.
Okay, thank you everyone who have asked questions.
And thank you so much to my interpreters as well, who've been great. Can we give them a big round of applause?